This is a lesson about absolute and percentage error. We are looking for ways in this lesson to quantify error, or the difference between what we expect something to have, what value we expect it to have, and what value it actually has. We call that error, and we call absolute error is just the size of the error. What is the difference between, for instance, an approximated value and its exact value? Um, Absolute error could also be the the difference between the expected outcome and the exact outcome or the actual outcome. It could also be the difference between the claimed value and the actual value. Some examples here I have are if we were to estimate the measurements of a room or sort of roughly measure them, maybe to um, think about how much paint we need to paint the walls, then you have a rough estimate, you have an approximation, and then you have an exact wall measurement or floor measurement. And so the error is the difference between that. The second example I have here is maybe you are a racer, a runner, a track runner, and you know the time that you want, your goal time or the time that you expect to get in your race. And so the error would be the difference between that expected time and your actual time. Obviously, sometimes that difference could be positive or sometimes it could be negative, but what we're really looking at with error is the size of the difference. And then another example of error is claimed versus actual. So for instance, when you buy a box of cereal and it says there's 16 ounces of cereal, how much cereal is there actually? So the claimed weight of the cereal versus the actual weight of the cereal. So those are some examples of error, and absolute error we just get by straight up subtracting those. So our equation for absolute error is just, write that, absolute error. We write it as the absolute value because we don't care about the direction, negative or positive. We just care about the size of the difference. So the absolute value of the value of the actual, the, I'm sorry, the difference between, yeah, the approximate value and the exact value. So it's just, again, it's the difference between the value of the approximated value and the exact value. So VA is approximated, and VE is exact value. And I mean, the truth is, even though we could sort of switch up those letters and imagine approximated could also be expected, as you saw earlier, or exact could also be actual, it doesn't really matter which one comes first because we're taking the absolute value. So what matters is that we find the difference between the two. So whatever difference that is, it becomes positive with the absolute value. And then the second kind of error we're interested in is percentage error. And that's just the size of the error, but with respect to the size of the actual value. And it's percent difference. The percentage error formula is the same thing, the absolute value of the approximate value minus the exact value divided by the exact. That's the only one really that matters. You want the exact value there on the bottom. Whatever difference we get, whatever the size of the error, we're comparing it to the exact value. And this might be helpful for things where we're dealing with large versus small quantities. So an example of this would be maybe you are estimating how long it's going to take you to run the 100-meter, and your actual time is a minute different than your estimated or your expected time. So that minute is very significant, especially because a 100-meter dash is a short race in the first place. Um, Versus if you're estimating the amount of time it's going to take you to arrive at your grandma's house, and you estimate you are a minute off, then that's a really small difference, even though both of those would be a difference of a minute. So the error, the size of the error, the absolute error would be the same, but the percentage error would be much different. The percentage error for the race, the size of the error is really large with respect to the actual race time, versus if you're driving 3 hours to visit your grandma, 1 minute is an insignificant difference. So let's see how to use these formulas. Here we have a situation where you estimate a fence length to be 70 meters, but its true length is actually 78.3. So find, correct to one decimal place, the absolute error. So for this, for absolute error, all we do is just subtract the approximate value minus the exact value. And again, order doesn't matter that much here, but for A, approximate is 70, exact is 78.3. We take the absolute value of that, which that difference is negative 8.3, but when you take the absolute value, it's just 8.3 meters. So that's the answer for part A. 8.3 meters is the error. For B, we want percentage error. So we just want to compare that to the exact value. And so we put 8.3, or that difference, over the exact value, 78.3. And we just divide, and 8.3 divided by 78.3 is, well, we're going to round here, but it's approximately 0.106. It said find that to the correct to one decimal place, so that would be 0.1, or sorry, just 0.1. And if we were to write that as a percent, that you move the decimal over 2 places, and that's 10%. So that's our answer there. All right, let's take a look at, oh, I guess I should, sorry, on that one, I'm realizing the one decimal place, if we're going to write this as a percent, then we'll just keep it like it is. We don't need to round anything off. That is 10.6%. And let's just take a second to see if that makes sense to us. 8.3 is indeed about 10% of 78.3. So our error is about, it was about a 10% error, 10.6% error. Okay, let's take a look at example 9. Alan wants to lay carpet on his 4.2 meter by 5.1 meter lounge room floor. He estimates the area of the lounge room by rounding each measurement to the nearest meter. So if he find his estimate of the lounge room area. So first of all, let's do that. Let's round both of those to the nearest meter. 4.2 would be 4 meters, and 5.1 would be 5 meters. So find the area of his room. Assuming it's rectangular, then it's just 4 times 5, or about 20 meters squared. The carpet costs $39 per square meter, so find the cost of the carpet using Alan's estimate. Well, 20 times 39 is 78. Is that right? 39 times 20 is 780. So that's about, or that is $780. Okay, so now find the actual area of Alan's lounge room. Well, in that case, we're going to use the exact values, the 4.2 and the 5.1. 4.2 times 5.1 and we get 21.42 meters squared. By the way, notice that's more, the exact value is more than the estimated value, so this is just sort of a side, a personal note. If you're ever doing projects like this, even if the numbers do round down, like 4.2 and 5.1 both round down, always round them up anyway, because you never want to have less than enough. You always want to have more than enough if you're buying materials for projects. So round up even if the values tell you to round down. Okay, so in this case, the actual area of the room is 21.42 meters squared, and now we want the percentage error in Alan's estimation. So for this, I'm going to go down here, part D, we want percent error, which we just do the difference, the absolute value of the difference between his estimated 20 and his exact 21.42 over the exact. On the top, that's 1.42 over 21.42. And we can calculate that. We get 0.066, which if we write that as a percent, that's 6.6%, moving the decimal over twice. So that is the answer to part D. Will Alan have enough carpet to cover his room? How should he have rounded his measurements? Well, I got ahead of ourselves by answering that question prior, but clearly when you're buying material, round up rather than down. And now we've reached our last example, example 10. The side length of a square is measured as 22 centimeters, rounded to the nearest centimeter. Use this measurement to estimate the area of the square. So here we are just going to take 22 and use our area formula. Area of a square is just side squared, or 22 squared, which is 484 centimeters squared. Part B, find the boundary values for the area of the square. Well, since the thing that was measured were the dimensions, we have to apply the plus or minus a half to the dimensions themselves, not the area. So in other words, the length of the square was approximately 22 centimeters, plus or minus a half, as was the width. So the length could have been as small as 21.5 and as large as 22.5. And same with the width. Now we're going to take, if we're asked to find the lower boundary for the area, in other words, what's the smallest area that the square could actually be? And that would mean we underestimated both our length and width down to as low as 21.5. So 21.5 squared, which is 462.25 centimeters squared. That's the lower boundary for our area. Our upper boundary, or AU, for the area would be, had the exact area actually been slightly larger than 22, up to 22.5, and that gives us 506.25 centimeters squared. You could write your answer like that, or we could write it as a double inequality, a compound inequality, where we say 462.25 centimeters squared is less than the actual area, which is less than 506.25. And then part C says, hence, find the maximum percentage error in the estimate. First of all, you need to know that hence means using your previous answer or the previous question. So that is always a clue that we're going to use something we just did. To find the maximum percentage error in the estimate, that implies there might be multiple percentage errors. Well, we've got multiple possible actual values. Let's highlight. We have a possible actual value as low as 462 and as high as 506. So let's see if those produce different percentage errors. Using our percentage error formula, let's see, which was the approximate value minus the exact value over the exact value. We're going to take our approximate value, which was 22, minus, oh no, sorry, it's not 22. We're talking about the area. So it was 484. That was the approximate. Minus, assuming our actual value is, our exact value is the lower version, minus 462.25. Absolute value of that, and divided by 462.25. And that gives us a percentage error. And then, by the way, you can go ahead and do times 100 if you want to here to give you your percent. But that gives us 4.71%. And I just want to make sure we see that this is from the lower area, the lower boundary of our area. Now we'll take the upper boundary of our area. The approximate value of the area was 484, but if the actual area, the exact area is actually 506.25, then we subtract that and we divide by the exact and we multiply by 100, and there we get 4.40. And that comes again from our using the upper boundary. So we can see these are two different percentages. The reason for that is we have the same difference, but the difference is over different numbers. We have a smaller denominator. So the difference is a larger percentage of that smaller denominator for the yellow, hence the larger percentage error. So the question asks, what's the maximum percentage error? Well, the maximum percentage error would be 4.71. That's bigger than 4.4. And so that's the answer, 4.71%.